question mark at the end of that, or you have to call it a theory of everything candidate. Okay? Your earbuds are making noise. I think that's a problem with my phone, and I might need to upgrade my phone because it's a secondhand phone with some issues. Okay. The modern era of physics began with two revolutions that took place in the early years of the 20th century. Class, quiz question, what are those two revolutions? Tell me, tell me, tell me. Hi, Austin. How are you doing? What do you think of simulation argument? I don't know. Is that the one where we are thinking about or asking about whether we all live in a simulation or not? The static, I hear it too. Sometimes there is static, guys. I think it's my phone. I think it's my phone. I think I need a phone that does not have this particular defect, but currently this phone does. I'm so very sorry. The static is unbearable, some people are saying. Okay, let's keep going. The modern era of physics began with two revolutions that took place in the early years of the 20th century. One of them involved the introduction of relativity, and it played a major role in the development of cosmology throughout this century, as in last century and really until now. The other major upheaval was the birth of quantum mechanics. By contrast, the implications of quantum physics for cosmology are still far from understood. Okay, so some people like Stephen Hawking actually have used quantum mechanics in a more bigger sense, as in to integrate certain things about black holes, which were traditionally or historically a classical object, if you will. They came from a general relativity or a classical prediction, but he incorporated quantum into black holes, right? So not everybody completely ignores that there is general relativity as well as quantum mechanics, I would say, but to a large extent, the classical physicists don't always consider quantum, and the quantum physicists don't always consider classical. Okay. So, in the world, according to quantum theory, every entity has a dual nature. In classical physics, two distinct concepts were used to describe distinct natural phenomena, waves and particles. Quantum physics tells us that these concepts do not apply separately to the microscopic world. Things that we previously imagined to be particles can sometimes behave like waves. Phenomena that we previously thought of as waves can sometimes behave like particles. Light behaves like a wave. So light actually has both wave and particle duality. By the way, if you, one little trick to remember which one light is going to be more like, if you're considering the very short wavelengths of light, for example, gamma rays, then you have more of a particle nature of light. Gamma rays are almost like particle light, as in photons. Being hit with gamma rays is like being hit with particles. Okay, very short wavelength, very high frequency, almost like a particle, right? And it does have particle nature. If you want to consider light as a wave, then think of it as the bigger wavelengths. If you have longer wavelength light, for example, radio waves, then it is more like a wave and less like a particle, right? So light, for example, has wave and particle duality, but how it shows up or how it manifests in the physical is what I just told you, which is that if you have longer wavelength light, it's going to manifest physically more like a wave. If you have shorter wavelength light, it's